This is Geometry, section 7.4, Similarity in Right Triangles. So we've talked about similar triangles in general. In this chapter, or in this section rather, we're going to talk about right triangles specifically. So meaning triangles that have a right angle in them. So first of all, we need to remember what an altitude is. So if I have a triangle like this, and I want to draw the altitude from this point right here, that means a line straight down that makes a right angle with the side opposite from it. The altitude is just a fancy word for the height of a triangle. So an altitude goes from a vertex and is perpendicular to the opposite side. So in a right triangle, the altitude does something kind of cool. If you draw in the altitude, so if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed, so this is an example down here. We've got a right triangle and we're drawing an altitude down to the hypotenuse, meaning the side across from the right angle. So we're starting at the right angle and drawing an altitude. So when I do this, when I cut this into two other pieces, it creates two other triangles. So these two triangles formed are similar to the original big triangle. So why is that, or how is that? So if we look at this triangle right here, we want to write the similarity statement between these three triangles. Note that there's three parts since we have the original triangle and then the two smaller triangles. So if this angle right here is 32 degrees, and we're starting with the fact that this is 90 right here, this is 90 right here because it's an altitude. It's drawn so that it's perpendicular, which means this is 90 right here also. If I just look at this triangle, to find this angle up here, we would add up 90 and 32 and subtract that from 180. That's going to give us 58. If I look at the entire big triangle, I have the same thing. I have a 90-degree angle, I have a 32-degree angle, which would make this a 58-degree angle. And then to find this last angle, if I look at this other smaller triangle, then I have 90 and 58, so the leftover is going to be 32. So I've got three triangles, all with a 90-degree angle, a 58-degree angle, and a 32-degree angle. So if I redraw these three triangles so that they're all facing the same way, that's going to help me write the similarity statement. What letters match up with what letters? So let's start with the big triangle. If I keep it in order, so I say the 90 is here, the 58 is here, and the 32 is here. If I look at the entire big triangle, the 90 is letter M, the 32 is letter A, and the 58 is letter H. If I do that for this triangle on the left over here, so draw it in the same order, 90, 58, 32. So now this triangle on the left, we're talking about here, the 90 is now at letter T, right here. So that's a T. The 32 is still at letter A. Whoops, this is an A. And the 58 is now at letter M, right here. So that's an M. Finally, the last triangle, so 90, 58, 32. If I redraw that one, now the 90-degree angle is also at T, just like it was for the second one. The 32 is here at M, and the 58 is at H. So, to write the similarity statement, it becomes a lot easier now. I just match up the three letters. AMH, ATM, MTH. So, AMH, the first one's already written in there. So AMH, if I go in this order, from here to here to here, ATM matches up with that, and MTH. So the reason for this is because of the angles. We said nothing about the sides. All we talked about was angles, so what we learned in the last section was that's called angle-angle similarity. If I compare at least two of the angles and they're the same, then the triangles are similar. So using this, determine the value of x. Well, each of these gives us a right triangle with an altitude drawn in. So let's just call this a 40-degree angle, which would make this 50. This would be 40. This would be 50. So if we put some letters on here, it might make it easier to line these up. We call this A, B, C, and D. Then we can draw the three triangles and match everything up. And there's actually an easier way to do this, but just to show you this way, first of all, we'll skip this one for now and then we'll come back to it using the easier way. So ABC is the original big triangle. So let's say the 90 is here, the 40 is here for all of them, and the 50 is here. Okay, so big triangle. 90 is B, 40 is A, 50 is C. We'll go this triangle next. So 90 is D, 40 is B, and 50 is C. Other small triangle, the 90 is D, the 40 is A, the 50 is B. So now we have to figure out, well, where do these x2s and 14s go? Well, anywhere I see D and B, so here, for example, that's x. So DB is x, DB is x. Anywhere I see D and C together, so here, for example, that's 14, and I think that's the only spot. And then wherever I see A and D together, only spot should be here. That's a 2. Okay, so we have to bring the side lengths with us when we draw out the similar triangle. So now we know these are similar. These two sides are going to compare to each other. These two sides are going to compare to each other. So I can just write a proportion. X over 2 equals 14 over x. This compares to this compares to this. And I know they're similar, so they need to be proportional. If I cross multiply this, x times x is x squared. 2 times 14 is 28. To unsquare something, we would take the square root of it. So this is just going to be the square root of 28, which is not going to come out evenly. We could change it to a decimal. We'll just leave it like that for now. Like I said, we're going to skip this one and come back to it after we do this back page. So the easier way to do it has to do with something called geometric mean. So you've heard the word mean before, meaning the average of two numbers or a set of numbers. It's a little bit different when we talk about the geometric mean. So for any two positive numbers, such as A and B, the geometric mean of A and B is going to be a positive number, x or anything, such that I can write this proportion. A over x is the same as x over B. So the geometric mean of two numbers is what I get when I solve for this x, if I set up this proportion like this. So in other words, if I wanted the geometric mean of, let's say, 50 and 2, I would set up this proportion, 50 over x equals x over 2. I would cross multiply this. So x times x is x squared. 50 times 2 is 100. To solve for x, to unsquare it, I would square root it, and then I would get that x is 10. So I would say that 10 is the geometric mean of 50 and 2. So this seems kind of pointless. So how it applies to what we just talked about, it actually does have a purpose, yes. So write the similarity statement for these three triangles. Again, let's just make it simple numbers. So 40, 90, and 50 all add up to 180. So if this is 90, we'll call this is 40 and this is 90. This would be 50. This would be 40, just like we did for the original triangle with the 32 and the 58. So if I match this up, ABC is the big triangle. So we're going A, B, C, which means we're going from the 50-degree angle to the 90-degree angle to the 40-degree angle. So let's do that for the other two triangles. Starting with this one, we'll go from the 50, which is A, to the 90, which is D, to the 40, which is B. And for this other triangle, we start at the 50, which is B, go to the 90, which is D, and then to C, the 40. All right, so geometric mean theorems say, there's 3 of them actually. So one of them says, if I take that altitude that we draw in to create these 3 similar triangles, so this altitude, the length of the altitude, is going to be the geometric mean between the lengths of the 2 segments that it cuts that hypotenuse into. So in a right triangle, the altitude from the right angle divides the hypotenuse into 2 segments. So we take this altitude, it cuts it into DC and AD. This is going to be the geometric mean between those 2 pieces. So in other words, if I write AD and DC, DB is going to be the geometric mean between those. So I write that in these two spots and the other two things that I'm finding the geometric mean between in the other two spots. This will make more sense when we do examples of it. So similarly, each leg of the original triangle, so the two sides of the triangle that are not the hypotenuse, each leg is the geometric mean between the entire hypotenuse and the chunk or the segment of the hypotenuse that's closest to it. So it cuts it into these two pieces like we said over here, AD and DC. DC is the piece that's closer to this leg, but AD is the piece that's closer to this leg. So this piece, BC, is the geometric mean, so I put that in two spots between the entire hypotenuse, AC, and the piece that it's closer to, DC. This leg, AB, is the geometric mean, so I put that in two spots. It's just the definition of geometric mean, so I put that in two spots. It's the geometric mean between, again, the entire hypotenuse, so AC, and the piece that this one is closer to. So now this is closer to AD. So again, examples. Let's go back to the one that we skipped over. So this is a leg of the original triangle. So we said that that is going to be the geometric mean. Whoops, so I'm going to put it two spots here and here. So it's going to be the geometric mean between the entire hypotenuse of the original triangle. So this is the entire hypotenuse, which it doesn't give me that whole thing. It gives me this piece is 8, this piece is 12. So the whole thing would be 20. So it's the geometric mean between 20 and this piece that it's closer to. So it's closer to this piece, so 8. When I multiply, cross multiply, notice how we ended up with something similar over here. We ended up with x and x in two spots and then two numbers in other spots. We could also apply the first geometric mean theorem to this triangle over here, and it would end up being a lot less work than drawing out these three triangles, creating a proportion based on the corresponding sides, and then solving it. So back to over here, if I cross multiply this, we get x squared, 20 times 8, 400, and then when I square root that, I'm sorry, 20 times 8 is not 400, so that won't work. 20 times 8 is 160. So when I take the square root of that, that doesn't come out evenly either. We could change it to a decimal, we could simplify the radical, but we'll just leave it like that for now. So back to the examples. More examples of geometric mean and how to use this. Okay, so note also that if you like the first way better, drawing out the three triangles, comparing all the sides, you can absolutely do that. This is just another way to solve the same problems. Okay, so starting with the first geometric mean theorem, the altitude itself is going to be the geometric mean between these two pieces. So x here and here, 48 and 27 here and here. When I cross multiply this, I get x squared equals, let's see, 1296. And when I square root that, we get that x itself equals 36. Same thing for y and z. So now y, let's change colors here. Y is going to be the geometric mean between the entire hypotenuse, which is going to add up to 75, and the piece closest to it. So y and y, 75 and 48. When I cross multiply that, do all the work, we get that y equals 60. The setup for z would be similar. So z is the geometric mean between 75 and now 27, because z is closer to 27. 75 and 27. When we cross multiply this and solve for z by taking the square root, we get that z is 45. Same thing over here for the last one. Altitude, geometric mean between the two pieces, so z and z, 45 and 80. When we cross multiply that, z is 60. Two legs are the geometric mean between the entire hypotenuse, so that all adds up to 125. So if I change colors for x and x would be the entire thing, 125 and 45, and then y would be the entire thing and 80, because y is closer to 80.